Today's topic, what and where are the tropics?
Hello, welcome to the tropics. Where are the tropics actually? The tropics are a zone of the Earth's circumference that is the central band or the latitude of the Earth. It actually covers a significant part of the Earth, about half of it in fact, by definition the area of the tropics is what includes the equator and also 23 degrees and 27 minutes north, which is called the Tropic of Cancer, and 23 degrees and 27 minutes south, which is called the Tropic of Capricorn. So this latitudinal band of the Earth encompasses the tropics, and it hasn't always been that area specifically. In the past it's been larger. For example, in the Jurassic period there are parts of North America, Western North America, that would have considered the tropics, and there was no ice on the poles at that period of time. And conversely, in the ice ages, the amount of Earth that was the tropics was reduced because of all of the cold climate that was on the Earth at that time. The tropics are typically divided into two broad different realms. I am here in what's called the neotropics, or the neotropical realm, and that includes Central America, like for example here in Nicaragua, also South America, and various islands that are in the tropics in the Caribbean and in the Atlantic.
So here we have a figure from your book, and it has the bands that I was referring to shown here. That is the Tropic of Cancer here, and the Tropic of Capricorn here. And you can see they're positioned on either side of the equator. So this is the area that would be considered the tropics and the subject of our class. So the location of the tropics has changed throughout time, and this figure in your book shows you an image of Western North America, hard to believe by looking at it, and the vegetation would have been considered tropical, but in other times the planet was cooler, like for example the Ice Age, and the amount of tropics was way reduced.
So again, welcome to the tropics. Here we are in a pre-montane forest in Nicaragua, and I have two words that come to mind when you talk about the tropical climate, and they are warm and wet. Last night it rained here. We have a little break in the rain for the moment, and it is warm. So regarding warmth, the temperature in the tropics is pretty consistent year-round. So unlike in the United States, for example, where you can have a change in the temperature month to month, here the temperature variation is not great year-round. It's pretty consistent. So regarding warm, there are exceptions, of course, to this. For example, if you think about Mauna Kea, the very tall mountain, volcanic mountain in Hawaii, receives snow because of its very high altitude. Regarding wet, well, the wetness, the rainfall, could be consistent year-round, where there's not much variation from month to month, but there are also areas where rain is expected in one season and not another. In fact, when the people in the tropics think about seasons, they're not thinking about temperature. They're typically referring to rainy season and dry season, if they have those. And so if there's a dry season, it could be that it's a relatively short dry season, or it could be a longer dry season. So that really depends upon the area that you're at. If it's a relatively short dry season, then the vegetation can remain green year-round. But if it's a longer dry season, then, well, the trees have an adaptation to be deciduous. Now, we actually use that word in the United States, but we typically refer to deciduous as when trees drop their leaves in the winter. Deciduous means when the trees drop their leaves, and here it's a response to being dry. So dry here. Now I'm in a moist tropical forest which receives about 3 meters of rain per year. However, it's extremely seasonal when that rain comes. And in fact, you're looking at a forest that hasn't seen rain since October, and it's now May. So the trees must have to adapt for this lack of rain and drying out, and one way to do it is to drop their leaves. So that makes them seasonally deciduous. So it's a adaptation to help keep water. And so you would find in the, they call them dry tropical forests, for example, in the dry season, you find a lot of trees that lack leaves and a lot of crunchy leaves on the ground that you walk upon. And the biomass is typically less in these drier tropical forests than the wet tropical forests. Now, if it's an area that doesn't receive enough rainfall, period, then it wouldn't be a forest at all. And you do find tropical savannas and tropical shrublands and tropical grasslands.
So the climate in the tropics, warm and wet, and the temperatures are fairly consistent. And we're looking at some data here from a location in Brazil. And the temperatures, you can see, are pretty consistent on average, greater than 75 degrees Fahrenheit or 24 degrees Celsius, and fairly consistent through the year, as you can see. Now, the rainfall, you can see that's a different story, and there is variation. This is a case where we've got a wet season and a dry season. So why is it warm? The reason that the tropics are warm is that they're basically getting more directly hit, more directly hit by the sun. And so the sun is a shorter distance from the sun to the equator than it is to more southern or northern latitudes. So it's more of a direct hit. And because the sun is shining more directly, it covers a smaller area and heats it up more intensely. On the northern hemisphere, as you see in this picture, there's a longer distance for the sun rays to travel, and plus the area that they cover is larger. And so all of that solar energy is more dispersed. Interestingly, because the sun is hitting more directly and there's little variation with season, the length of the day is consistent in the tropics. A 12-hour day, that is. It would be very common for the sun to rise at 6 a.m. and to set at 6 p.m. year-round, for example. So another question, why is it wet? The reason the tropics are wet is because, because there's high rainfall and high humidity. And that precipitation can either be consistent. In some locations in the tropics, it's just wet year-round, or it can be seasonal, as you see here in Brazil. So understanding a little bit more about the wetness, because we know the sun is hitting the equator more intensely, that means that the air then around the equator would heat up. And with that heating of the air, the moisture in the air is also heated and they rise. So this moist air rises from the equator. And as it gets further away from the surface of the earth, this air, this moist air starts to cool. And when the moist air cools, that's a conditions that are perfect for the water vapor to become liquid, and then it would rain down on the equator. So heated, moist air, cooling, falling as precipitation. Now, because of the air patterns that predominate on our planet, um, the in particular, what happens on our planet is that the air mass will rise from the equator and will either go to the south or the northern hemisphere in large masses. So we have a circulation of air generally, and these large blocks emanating from the equator. So moist air that doesn't happen to fall right down the equator, that moist air would then go south or go north. And as they do that, it's cooler in the southern and northern hemisphere. And so the water vapor then would become uh, liquid instead and fall as precipitation. So making not just on the equator, but the areas just to the north and the south equator also uh, susceptible to a lot of rainfall. Now, if this happens enough, then the water vapor is basically going to become depleted, and that's what we see. By the time the air masses reach the 30 degrees north or 30 degrees south, at that point, the air is depleted, and so we don't have uh, precipitation happening. And indeed, it's in these areas that we find the great deserts of the earth. So let's now turn our attention to the Holdridge life zones. This is a proposal put forward by Leslie Holdridge in 1947, where he hypothesizes that one can make a connection between plant distribution and climate. And based upon three climatic variables, Holdridge proposes that you can predict, and he created a hexagonal diagram to do that. He could predict what type of plants you might find based upon the climatic data. And the reason he says this is because, well, plants are sessile. That means that they can't move. And so a plant that is in a particular climate is likely to be adapted for that climate, because any plants that are not adapted to that climate, well, they're not leaving offspring. They're not going to be found on a long-term basis in any particular place unless they are suited for the climate. And so this gives you a sense of how evolutionary pressures can act on vegetation. And so with the Holdridge system, and given that climatic data, you can predict the terrestrial ecosystem. You can predict the types of plants you'd find in any particular place on the planet if you have that climate data. So what variables are we talking about? What type of climate data? What we're referring to is the biotemperature, number one here, which is shown on this part of the diagram, and it's in bands. Number two, annual precipitation, and that's measured in millimeters here along this side of the diagram. The amount of precipitation, very low to very high. And number three, the potential evapotranspiration ratio, which is shown on the left side of the triangle. So regarding the temperature, you can see in these bands the temperature in Celsius from high temperatures to low temperatures. On either side of the diagram, these bands are present. And the reason that there on both sides of the diagram is to really point out that there's a correlation here between latitude and altitude. So note how the temperatures correlate with both the latitude and the altitude. That is, the temperatures at higher and higher altitudes get cooler and cooler. You know this. Going up a mountain, the temperatures will go cooler and cooler, like, for example, going up Tahoe or Mount Shasta. Um, and there's different bands of vegetation that go along with that. The temperatures going away from the equator to larger and larger latitudes, that is closer and closer to the poles, also will decrease in temperature. And so that's represented on this diagram. And so there's a correlation between the zones of going up a mountain and the zones of going away from the equator. Now, the third side of the triangle on the left side, if you recall, was potential evapotranspiration ratio. And that's what I'd like to talk about in more detail now. But if you could just for the moment notice that the numbers for this ratio go from very small to large, like 32 is the highest one that they listed. And this ratio represents how arid or how humid a particular ecosystem might be. So the potential evapotranspiration ratio is the ratio between the mean potential evapotranspiration and the mean annual precipitation. So let's just talk for a minute about what this term evapotranspiration might be. It's the way I think of it is that it's evaporation and transpiration. So evaporation would be the water rising from evaporation, perhaps from the soil, and becoming vapor. And transpiration is similar, but it involves a plant. And so it's water that's traveling through a plant, and then water that will leave the plant through its leaves and go from liquid to a vapor. And so includes both evapotranspiration. Now, mean potential, that means the average potential ability for evapotranspiration in that particular climate. So the amount of water that can potentially, there's the potential, enter the atmosphere from the evaporation from soil and from the transpiration from plants. So greater solar energy striking a location is going to mean more potential for this evapotranspiration event. So how does that then correlate to this third variable? Well, that's the first part of our ratio. The second part of our ratio is the mean annual precipitation, or how much is it raining, or how much is it snowing or hailing, so how much precipitation. And so if this ratio is a very low value, that means that this is a great deal of precipitation with respect to the potential for evapotranspiration. And so that's going to mean a very humid region. Whereas if this is a very high value, we've got a lot of evapotranspiration and not so much precipitation. And so that's going to be a super arid region. And so these three variables then work together to create this system of organizing ecosystems. And so in any particular place on the planet, you can collect this climate data and then determine what type of vegetation you might find there. And you can see that in his system, he's got rain forests versus wet forests versus moist forests, whereas rainforests would receive, relatively speaking, the most precipitation. And depending upon the amount of precipitation, the potential evapotranspiration ratio, you'll get other climates, and that can change depending upon the position of the altitude or latitude as well. So pretty cool system, and over the time it's held the test of its predictive value. So I hope that you see here that the tropics have quite a variety of ecosystems, and just a brief survey of some of the significant ones. I want to discuss savannas, like for example here in Tanzania, you can see quite an impressive collection of wildebeests. Another shot from Tanzania. So the savanna is a tropical ecosystem that's dominated by grasses and scattered trees. So you don't see a whole lot of trees. It's not enough to call it a forest. The tropical dry forest does have more trees than a savanna, but because the rainfall is so seasonal, it has significant portions of the year that are dry. And so that's going to limit the vegetation that can live there. So these aren't as lush as some of the other forests. That one's Venezuela. Here's Australia. That's a termite mound. Another image of a dry tropical forest in Australia. Now, a moist forest, according to the Holdridge definition, is a forest that receives 200 to 400 centimeters per year.
And a great example of a moist forest would be Cabo Blanco. Welcome to Cabo Blanco Absolute Reserve. Such a beautiful place. We are situated on the tip of the Nicoya Peninsula in Costa Rica and bordering the Pacific Ocean. And this place is, weather is seasonal here, but consistently it's hot and humid. However, the classification of the Holdridge classification is moist tropical forest, and that has to do with the average temperature and the average amount of rainfall. On average, the temperature here is 81 degrees Fahrenheit or 27 degrees Celsius, which seems just about accurate for today. And it receives 10 feet of rainfall, an amazing 10 feet, equivalent to 3 meters. But what's more amazing is the fact that 10 feet of rainfall does not occur evenly throughout the year. It actually is dry here for a significant amount of time. In fact, it's May and it has not rained here significantly since last October. So for 6 months of the year, it's extremely dry. And then for 6 months of the year, that 10 feet of rainfall comes. And so it makes it a very challenging situation for the organisms that live here. Very dry, then very wet. Yet, life is abundant here. Wow. What's with all this leaf litter? Stopping here to tell you about a group of plants that does particularly well in the moist tropical forest, able to deal with the seasonality. And that group, of course, are the palms. The royal palm, with these enormous leaves, is commonly used by the locals for creating thatched roofs. Here's a new one. Terrestrial bromeliads. Now here's a plant that's adapted to going for long periods of time without water.
But when it's the wet season in a moist forest, it can look quite lush, like you see here in Trinidad. And this is another moist forest image, this one from Ecuador. So according to the Holdridge system, we now can separate out different types of what was, I think, typically before the Holdridge system anyway, referred to as rainforest. And probably in common terminology, all three of these would be considered a rainforest because they're all very lush. They all have a lot of vegetation and lots of diversity of plants and of animals. But technically speaking, if it's 200 to 400 centimeters a year, that's a moist forest. 400 to 800 centimeters a year is a wet forest, and greater than 800 centimeters a year, that is, according to Holdridge, a rainforest. Um, this is actually quite rare. So a Holdridge rainforest occurs on very few areas of the planet. And probably from a photo couldn't be distinguished from a wet forest, which still gets quite a bit of rain. So here's a wet forest from Malaysia.
And the type of forest that you can see here, it's a rainforest, and that is based upon the amount of rainfall that this area receives, which is pretty much daily. And so the area is very, very lush.
All right, Keegan, why don't you come down?
Well, I can stay up here, and then. Oh no! I don't think you can stay up there anymore.
We'll do this in a minute. Okay.
And then, depending upon its elevation, another significant tropical habitat are the montane forests, that is, going up further up a mountain. And one of the most impressive montane forests are those of cloud forests. And so cloud forests are forests that are immersed in clouds, are continually moist, not necessarily from rain, but from moisture-laden air.
So I'm delighted to be here in the Monteverde Cloud Forest Preserve, one of the most famous places to come when you're in Costa Rica.
Yeah, and hot, right? But it does rain less here than in the rainforest. We have an average of maybe 2.5 to 3 meters of rain a year. That I know is like 9 feet, more or less, of rain every year here. But it's less than in the rainforest. So it's different. That's another difference. Of course, the clouds is another difference, and the vegetation. So as we go, you'll start to see how it looks different. Maybe we can point out some things. Over here, we can point out some things. So, for example, did you see much of this in La Selva? No. Moss? No, right? Doesn't grow as much over there. And this, as we get it deeper into the forest, you'll see more and more plants growing on the trees. That's another big difference with the rainforests. Yeah. Okay.
So looking at a cloud forest here in Ecuador and the abundant epiphytes that occur there. And this is the perfect environment for growing epiphytes, and that is plants that live on plants, because they can get their moisture directly from the atmosphere and they don't need to draw it from the ground.